Welcome to the first chapter of Physics 1. As any physics course, I would like to start with the study of motion in one dimension. These are the three main topics of this part. I will show you over a dozen of exercises in which first objects move with a constant velocity, then we're going to have these objects either speeding up or slowing down, and finally we're going to study free fall. This is objects that are accelerated due to the action of gravity. Once again, welcome to this course, and I hope you enjoy all the tricks that I will show you for solving all these kind of exercises. Let's get started. During the Apollo missions, a collection of retroreflectors were installed on the lunar surface, located 380,000 kilometers from Earth. Estimate the time for a laser pulse shot to the moon to bounce back if the speed of light is 3.0 times 10 to the 8th meters per second. Alright, so this is our first exercise, and I want to show you my personal recipe. You will see this over and over again, but I hope that this serves as a guide so you can solve any physics problem using this recipe. So the step number one is to have a look at all the quantities that are given in the exercise. In this case, we know the distance between the Earth and the Moon is 380,000 kilometers. And second, we know the speed of light. We're being asked about the time. This is the other very important quantity because you don't want to start just writing equations. You want to write the formulas that are useful for solving the problem. So to answering the question you're being asked. In this case, time. The next step is to draw a little cartoon. That always helps. And for this cartoon, the first thing that I always do is to select my coordinates. Since we're studying motion in one dimension, one line is enough. This line will represent the x-axis. You give it a direction, which means you select in which direction x will point. In this case, I selected to go from left to right. This is the meaning of this arrow. And you need to put the origin somewhere. So the origin means where the coordinate x is equal to 0. The next step is to see what really happens in the situation. In this case, we have the Earth, where we have some source of light, some very intense and powerful laser pointer, if you want. And somewhere over here we have the moon with the retroreflector. Retroreflector is just a collection of cleverly designed and arranged mirrors, so you can imagine this is a mirror. So here is the moon, and on the other side is Earth. In the exercise, we have a beam of light that is being shot from the Earth to the moon, which will bounce back. Here we can take advantage of the symmetry of the problem, because the light will go to the moon and back, and it will take the same time to go from the Earth to the moon as the time from the moon to Earth. So I'm going to focus only on the part where the light goes from Earth to the moon. Let's put the moon at some distance d. Now the value of this distance, I will just call it d for now. And the laser beam will do the following. It will move on a straight line until it hits the mirror. And it will take some time t. And this is the time that we need to find. In the question, we want the total time, so we want it to go all the way to the moon and back, but we know that the total time will be just twice the time to go from one side to the other. So I will only focus on this quantity, and then I will simply multiply by 2. In the study of uniform motion, when there is no acceleration, there is only one formula that we can use, so this makes it quite simple. That formula tells us that the position of the object at any time is going to be the initial position plus the velocity times the time. The initial position refers to the point where the object starts. In this case, it starts from the Earth. The object in our case is just light, is the beam of light. It starts from Earth, where we have selected the origin to be. So this is not a coincidence, this is in fact a choice. We have chosen the origin of the coordinate system to be on Earth so that this term here goes away. It's just 0. The initial coordinate is 0. And this is v times t. Now this tells us the position of the beam of light at any time. We're interested on the moment when the light goes all the way and hits the mirrors on the moon. In that case, the x-coordinate is equal to d, which is the distance between the Earth and the moon. So I will set this x to be equal to d, equal to vt. And now I can, from this equation, I can solve for t, which is the quantity that I'm looking for. If I divide by v on the two sides of the equation, I get on the left, I will get d divided by v, and on the right I will get v times t divided by v, but the v divided by v will simply cancel. That's the whole purpose of dividing by that, because v divided by v is just 1, independent of the value of v. And here we have it. This is just d divided by v. And now we simply need to plug the numbers. But before I do that, I would like to make a few comments because this can happen in several situations. Units are extremely important. They will appear all the time, and you will hear me say this several times. Units are very important. We find a little issue here. The distance between the Earth and the Moon is given in kilometers, whereas the velocity is given in meters per second. So the unit of length is not the same. If you want to solve an exercise and you want to get the right answer, you must use the same unit for different physical quantities. That means length should always be in meters or in kilometers, in any unit you want, but you must use the same unit all the time. The same applies for the time, because sometimes the time will be in seconds, sometimes it will be in hours, sometimes it could be in minutes. In the future, you're going to find situations in which the mass is given sometimes in kilograms, sometimes in pounds, or the velocity could be meters per second, kilometers per hour, or miles per hour. You must be consistent and units must be the same all the time. Alright, with that clear, I need to write the distance in the right units. So I want to use meters. So the distance, I will continue here on the right, the distance is 380,000 kilometers. This is a lot of zeros, so we can write this using scientific notation. This is the same as 3.8 times 10 to the 5th power kilometers. Now, this is the unit that I would like to transform into meters. Kilometers, we need to know that 1 kilometer is 1,000 meters, or 10 to the 3rd power meters. Kilo always means 1,000. So 1 kilometer is 1,000 kilometers, 1 kilogram is 1,000 grams, and so on. Alright, so I want to plug this here because I want to replace that, and I get 3.8 times 10 to the 5th times kilometers, which is 10 to the 3rd meters. These powers of 10 can be combined, and for that we simply add the exponents. So this is 10 to the 5 plus 3, this is 8, so this is to the 8th power in meters. So now we have the distance between the Earth and the Moon in meters, which is what we need. Great, so now we can use the formula we derived before here at the bottom left. I will draw a line here. And the formula was time is d divided by v, where d we just found is 3.8 times 10 to the 8th meters divided by the velocity of light, which is 3.0 times 10 to the 8th meters per second. So here we find that the units of length will cancel because you have meter divided by meter, so that meter cancels. And the only term that survives is the second. So 1 divided by second is just second. So this is exactly what we want for time, because time is being measured in seconds. And the value we find here, we can get it in our calculator. We have 3.8 times 10 to the 8th divided by 3.0 times 10 to the 8th. This is 1.3 seconds. So this is the time that it takes for the light to go from the Earth to the Moon. But the question is, estimate the time for the laser pulse to bounce back. In other words, we want the total time. We want the time that it takes since I turn on this pulse of light, how long it will take for this laser pulse to bounce back to me. So I will see it again in a time t, which is not exactly this 1.3. This is the time that it takes to get to the Moon. It will take exactly the same time to bounce back. So the time, we can call it total. So the total time is just 2 times t. So this will be 2 times 1.3 seconds, which is 2.6 seconds. In other words, if you could have a powerful enough laser pointer and you shoot this laser to the Moon and you get it to hit one of these retroreflectors, you're going to see this same light bounce back to you 2.6 seconds later. And this is exactly what we do. This is the purpose of these retroreflectors left on the surface of the moon by the Apollo astronauts. In the next exercise, we're going to look at some concepts that sometimes are mixed. I'm talking about distance and displacement, as well as average speed and average velocity. So don't miss that.